All right, thanks for having me. I'm Niklas, and today we'll talk about S1, simple test time scaling. And this was a joint work with an amazing team, and we'll go right into it. The genesis for this work was OpenAI's O1, which they released in September 2024, and they said that this was a new reasoning language model, and we were trying to figure out, okay, how do we reproduce this in the open? How do we get a reasoning model that's really good and everybody can use and download and learn from? By the way, feel free to interrupt me during the talk if someone has a question or feedback. Just jump in right away. And so from the O1 blog post, they had some pretty big performance jumps on these reasoning tasks. Amy, code forces, GPQA, which are pretty difficult reasoning tasks. Amy for math, GPQA is scientific questions. And the other part that was really exciting was the test time scaling. So not just was the performance pretty good of the model, if you gave it more compute, both at train and at test time, it would get better. So I really want to highlight this. There were two axes that were exciting. Good reasoning, and then test time scaling, getting that performance to be even better as you provided more compute. And interestingly, there's two compute scaling axes here. There's the training compute. So on the left side, they give it more training compute and it gets better. And on the right side, also giving it more compute than at test time after training and it gets better. So we have two scaling axes, which is very interesting and different from previous scaling paradigms. And so taken together, I think these two are really powerful. If you have really good reasoning and a model that can think through problems, and then you give it the second part, test time scaling, where it can think through these for a very long time. Ideally, you can somehow control how much time you want to give it. Then maybe we have a shot at solving some really hard problems, say Riemann hypothesis or some really hard unsolved problems where you need to be really good at thinking and probably does take some time. So you need to be able to let the model think for a week, a month, however long it might take. I felt this was very exciting. So the question we ask in this work is, what is the simplest recipe to get these two components, to get the reasoning and the test time scaling? And the answer we came up with is S1 simple test time scaling. And the work really consists of two parts to address each of them. We create a data set called S1K of 1,000 extremely challenging reasoning problems that invite the model to think with thinking traces as well in them. And then after training on this data set, in order to let the model scale at test time and vary its test time compute, we use budget forcing, which is a very simple technique we'll cover in a bit. And together, there's good data that elicits reasoning capabilities in the model, plus the test time scaling leads to a model S1 that somewhat reproduces O1. It actually performed better than O1 preview. And you have both of those capacities, good reasoning performance and test time scaling. So let's go into each of the components. First, the data part. So on the data side, we collected 59,000 questions that were really hard. Here's an example from a question we collected at Stanford. S1 prob is what we call it, where it's really hard statistics or math problems that are actually used in, I think, the qualifying exams for PhD students. We also collected some brain teasers that are often used in interviews and various other really hard sources, physics, physics tasks, USACO, which is, I think, computing Olympiad, very hard tasks, crossword puzzles, tasks that you probably need to think a lot before you can solve them. And then what we do with those 59,000 is we use three quality filters to reduce them to a smaller set. The first one is quality. The second one is difficulty, and the third one is diversity. So three kinds of filtering methods. And the reason we want to filter it down is because we want the simplest recipe. We want to really show what is the max you need in order to get such a reasoning model. So a very small data set, ideally. And the way we pick these three filters is pretty intuitive. I think you probably want, obviously, the data to be super high quality. So there's some basic formatting things we filter out there. Then, of course, you want very hard questions. So we filter for difficulty. And then finally, in order to cover various domains and make sure it generalizes diversity. And diversity is just we make sure that we don't just pick the math questions, but we pick math and physics and biology and from various other fields. Great. So then we have our final set of 1,000 samples. And now, at this point, these are only questions and sometimes solutions, but mostly just really hard questions. And in order to get the model to think in the simplest way, we'd like to just use supervised fine-tuning, just fine-tune it, train it directly on those questions, but we need the thinking traces or reasoning traces together with them. So we take some existing models and just distill reasoning traces from them. So for example, we feed all of these 1,000 questions to Google Gemini and get thinking traces from it, and then also from DeepSeek R1. And they give us very long reasoning traces. So here, for example, we have a problem where an often repeated fun fact is that humans produce more power per unit volume than stars. And so there's some reasoning question. It then goes, what would its surface temperature be if they produce the same amount of power per unit? And then S1, the Gemini data goes to that problem, and then the DeepSeek R1 also tries to solve that problem, and we get a very long reasoning trace from each one. And here's some statistics on how they differed and how long they look like. So we have just a density plot, and the x-axis is the length of the reasoning traces, and DeepSeek R1 produced very long traces. The Gemini ones turned out to be not super useful because they're pretty short. We wanted them to be long so that the model can really has time to think. We wanted to test time scale, think for very long, if necessary. So with these traces in hand, we are ready to go further and train. Here's another quick overview of how they look like in terms of diversity. So we cover a lot of different fields, geometry, real functions, biology, number theory. So really covering a wide variety of problems. Obviously, it's easiest to just pick problems from math. There's a lot of very hard math problems, but we want these models to also reason for fields like astronomy and so on. So we make sure that even though it's harder, we also cover problems from there. And then before going into training, let's look at the second part of the recipe. So now we've got the data, which is those 1,000 samples. Pretty simple, really. We just make sure we have really hard 1,000 samples, 1,000 questions with reasoning traces. And now, after we train on this data, how do we get test time scaling in the model? How do we get it to think for very long and for as long as we want it to? And this is where we come up with budget forcing. Here's an example of how it works. So let's say we have a somewhat difficult question, maybe rather easy. How many are in Raspberry? And then the model in its reasoning trace or thinking trace thinks through this question. So it goes, let's break down the process of counting the letter. Letter counting is actually pretty hard for these models because of the way the text is tokenized and fed into the model. So it is somewhat challenging. And then it goes through this question, and here eventually it says the number of R's in Raspberry is 2. And it wants to finish there and finish its reasoning and just provide its final response. And what we do instead is when we want the model to think longer, and this is the key here because we like to be able to control how long the model thinks, we simply do not allow it to finish and end its generation and move on to the response phase, but we just insert this wait token, which is marked in red here, and then let the model continue generating. And funnily, because now it has this wait in its current thinking trace, it'll be, okay, it has to generate something that makes sense after wait. And what would make sense after a wait is probably reasoning more, questioning what it has done thus far. And that's what it does. So it goes, let's reread the question carefully. It asks how many are in Raspberry. And then it goes through the word one by one, counts again, and gets to the right solution, which is 3. So it first miscounted, but then by inviting it to think longer, by not letting it finish, but just inserting wait, we get it to correct its answer and arrive at the final correct response. And then we let it finish, and it moves on to the response and says, my initial answer of 2 was incorrect. Due to a quick reading, the final answer is 3. So what we do to let the model think longer when we want it to think longer is simply not allow it to produce the text that means finish my current thinking, right? So when the model generates answers to these questions, we have these special tokens like beginning of thinking and end of thinking that we use to distinguish when it is in its thinking phase and in its response phase. And we simply do not allow it to generate end of thinking. And rather, when it tries to do that, just insert wait to invite it to think longer. And then, of course, it will generate something that's reasonable after wait and question itself and sometimes arrive at the actual correct answer. Inversely, when we want it to think for a shorter amount of time with budget forcing, what we do is we just force the budget. So say we just wanted to end after one sentence. So right at the beginning, after let's break down the process of counting the letter R in the word raspberry. If we wanted it to finish right after then we just directly insert the end of thinking, and it'll just be forced to finish there and move on to its response, and it'll provide its best current guess of what the answer is. So that way we can, ahead of time, before asking the model, we can decide, okay, how many tokens do we want the model to think for? Is it 10,000? Is it 50,000? And at the end of the day, it depends on how urgent is getting an answer. Probably if you're asking a model to solve the Riemann hypothesis, it's not very urgent. It's fine if it gets us the right answer in a month. But if you ask it to solve an urgent user question about some problem they're facing in a production system, then you probably want to give them an answer really fast. So based on that, you can decide how to set this budget. And then if the model reaches the budget and still wants to think, you just force it, you cut it short and put in the end of thinking trace. Versus if it thinks longer, if it wants to finish and you want it to think longer, then you don't let it do that and you just insert wait. And this is pretty simple, I think, but feel free to interrupt me if there's any questions. And together now we have the data, which elicits the reasoning capabilities, and we have this very simple test time scaling method that allows us to control how long the model thinks. There's some other things we tried I want to briefly mention. So another idea is we had is conditional length control, where we tell the model in the prompt, think for X amount of tokens. And then you could still add on budget forcing on top. If it doesn't follow the instruction, then you could still force it to do that. But with just budget forcing, you don't necessarily also have to tell the model what the actual budget is. You can just force it behind the scenes. And another post hoc method we tried is rejection sampling, where we just generate many times from the model and then just pick the ones that fit into the budget we want. And we'll look at some results later, but this is also interesting what this reveals. But it is not a method that you could use from the beginning, because obviously you only want to generate once. You can't just generate until it fits the right length at inference when it's being used. Great. And in order to think about how good a test time scaling method is, we consider 3 criteria. So one is we want control. We want to be able to control how long the model thinks. 2 is scaling. We obviously want more thinking time to lead to better performance. Otherwise, it's a waste of compute. And 3rd, we care about, okay, what's the actual max performance we can reach with this test time scaling method. So I think these are really useful to contextualize different methods to do test time scaling. So with budget forcing, for example, we get obviously perfect control. We can directly set a token amount. because we'll just force it. We'll look at the scaling in a little bit, but it does seem to scale with more test time compute. And then the max performance is also pretty good, which we'll take a look at. And here's, again, the O1 plot on the right side where it does have positive scaling. We don't know exactly about how controllable it is since they didn't share it, but you do have, I think, now in the API, they have a parameter to somewhat control it. And then the performance it reached is would be the final performance at the end around 80, which is probably good. Great. So let's look at the actual experiments, training and results. How well does this data work? How well does budget forcing work? So we train on a Quen model, which is a pretty decent open source model. We only use 16 H100s, which is very little, and the training only needs 30 minutes. So again, the goal was to create the simplest recipe. So we want this to be something that pretty much everybody can do to get a quick reasoning model. And training on 16 H100s for 30 minutes is pretty accessible. I guess if you only had 8 H100s, maybe it would take an hour, so you could probably also do it with less GPUs. And then we compare to a bunch of other models. So in our training, we simply do a supervised fine-tuning, SFT, for distillation, right? So we take those reasoning traces from other models, take exactly 1,000 of them, and then we just fine-tune on them, next token prediction with the Quen-based model, and that becomes our S1 or S1.1 model. And the reason we do SFT or distillation here is because it is very simple. If we were to do reinforcement learning, then that would be a lot more complicated and involve more infrastructure. And if we really want the simplest method that's very accessible, then we probably should go with supervised fine-tuning. And there's some other models that also did fine-tuning that we'll compare with. And then there's some models that do SFT plus RL. So notably the DeepSeek R1 model, they also did reinforcement learning, which probably can get you to better peak performance, but it does add a lot of complexity, as mentioned, infrastructure-wise. So it's not the simplest way to go about it. And then there's some methods that didn't disclose what they did, but we'll take a look at them anyways. So this is a performance plot from when we released. So on the y-axis is accuracy on Math 500, which is this difficult math task. And then the x-axis is the number of examples seen in training. And so we only trained on 1,000 examples for reasoning, which is very few. And the model reaches around 95 on this task, actually better than all other models in this plot. So there's these other SFTs, and even O1 Preview and O1 had a lot lower performance. So those results were pretty strong. And I think the one key intuition to take away from this is that a lot of the capabilities in LLMs, they already are in the model from this large-scale pre-training. When you want to fine-tune it for a certain behavior, say reasoning, you don't necessarily need a ton of data. It can help to have some extra data, but you can just elicit those capabilities that are already in the model, just slightly shift how it produces its output, and you can actually get really good performance. So say you wanted a model to follow instructions or to always respond in poems or things like this. You don't need much data for that if you fine-tune a large pre-trained model. And then here's another plot on the test time scaling. So this one here is mostly focused on the reasoning capability, which is what we wanted. We wanted really strong reasoning performance. But then how does the test time scaling look like? Does that reasoning performance improve with more thinking time? So on the y-axis, we have the accuracy, again, on 3 difficult reasoning tasks. I think these are the exact same 3 we saw at the beginning from OpenAI. So we've got Math 500, which is, again, pretty difficult math problems, another math competition, and then GPQA, which is science questions and physics and biology and so on. And on the x-axis, we have the thinking time in tokens. So this is how many roughly word units does the model produce to arrive at its answer. And clearly, the more time we give it, the better it performs because we use budget forcing. So it reaches decent performance on all of these. And we'll take a look at how this works behind the scenes in a bit. Actually, right here, which is that, So let's take the middle one. So Amy, we again have the accuracy on the y-axis and then the thinking time on the x-axis. And now if we look at, okay, what is actually happening in each of these dots here? The first few, we're forcing the model to have a certain amount of thinking time. So for example, for the second one, we say, okay, you only have 2048 tokens. We need an answer quickly. And then it reaches around 30% accuracy on this test task. Then the second one is 4,096 tokens. So we give it twice the amount of thinking time. Its performance improves to 42% or so. And then toward the end, where we wanted to think for longer, we do not allow it to produce end of thinking. So ignoring end of thinking. And then we just insert weight for a variable number of times. So 2 times is this dot. And then if we do it 4 times, it does improve a little bit, roughly to 60%. And then 6 times here, it actually stays at roughly the same level as before. And so for each of these, we append weight and force it to continue reasoning when it actually tries to stop. So it doesn't always help. Sometimes the model goes, we insert weight and then it says something along the lines of, wait, I should recheck it. But actually it's correct. Let me finish. Like it might not always go and actually change its answer, but quite often it does. So this is how this looks like in detail, and it's similar for the other two, for Math 500 and GPQA. Another thing that's very interesting to think about it is there are really two axes for test time scaling. You can either scale sequentially or in parallel. So sequential scaling is what we're doing here. We let the model think for longer. So it all stays one sequence, and what comes later depends on what came before. Parallel scaling, on the other hand, would be we launch the model multiple times in parallel, and then we just aggregate its answers at the end, maybe average them or something. And so the big advantage of parallel scaling is that you can get to a final answer faster because you can just launch more in parallel. But as we show in this plot, it doesn't scale as well as sequential scaling. So on the y-axis is performance on GPQA again, which is these science questions. And then the x-axis is the total number of output tokens. So let's start with parallel scaling at the bottom. Here we use majority voting, which means that we just generate many times in parallel, and then we take the most common answer of the model. And this is usually better than just generating once because you get rid of outliers where the model might have had a bad generation and got to a wrong answer. And as we give the model more compute or more output tokens for parallel scaling, it does definitely improve. At the end, at the 6 million mark, it kind of flattens out. And sequential scaling, on the other hand, has a much stronger slope. So it starts off already pretty high, and then it gets better with a much stronger slope. Now, the intuition why sequential scaling, I think, is generally preferred over parallel scaling is that with sequential scaling, you get the model to correct its mistakes, ideally, versus with parallel scaling, it might make the same mistakes multiple times in parallel because it doesn't see what the other models have generated. So you end up potentially wasting a lot of compute on the model, making the same mistakes repeatedly in different generations. So those are the trade-offs here, but they're not exclusive. You can definitely combine both of them to get even better performance. So you could do sequential scaling and then just launch the sequentially scaled model many times in parallel and do majority voting across the results, for example. And that would probably get us a performance that's even in the upper right here, even better than both. Great. We did some data ablations too. So as mentioned earlier, we had those 3 filters: quality, difficulty, and diversity. And so we checked how does performance change if we only use one of these filters. So for example, the 1000 random is sort of, we did the quality filters and then just take 1000 random ones. 1000 diverse on the second one, the third row here, is we only use the diversity filter, and then 1000 longest is we only take the most difficult ones, and length is our proxy for difficulty. If the reasoning trace is very long, then it's probably a hard problem. And we don't have to go into the numbers in detail, but the takeaway here is that using all 3 filters combined leads to the best performance. Individually, if we just look at the Amy column, they're all not as not as strong, the first three. And one other interesting point here is that actually training on the full 59,000, full 60,000 is about the same as our 1,000 data set. So it's maybe slightly better on Amy, a little bit worse on Math 500. So you don't get that much better by adding so much more data and more compute. So the simplest method, S1K, very simple, very few samples, is already really, really good. If not just as good as using 59 times more data. Great. And then some quick scaling ablations. So we tried these other methods we briefly mentioned before, token control, rejection sampling, and then use these metrics that we discussed, control, scaling, performance. I think the quick takeaway here is that budget forcing, BF at the top, it's pretty good because it gives us perfect control. So we can exactly control how long the budget is. The scaling is good, so it's positive. So more budget gives it better performance, as we saw in the plots before, and we reach a pretty good final performance here. I think this is Amy 57. So overall, this is a really decent method, but it can be combined with others. And I think this is what we see now in a lot of the deployed models. So maybe some of you have noticed if you use ChatGPT and it thinks, you get an option to say answer now in the interface. And they added this recently, and it's essentially budget forcing behind the scenes, I think, where if you press that, then they'll just force in the end of thinking token and it'll generate an answer right away. And Claude also previously had in their API a way to directly set a budget. They still often use these low, medium, high reasoning efforts, which is more fuzzy. You don't get a direct budget, but sometimes they also let you force an answer with a specific token budget. Great. Some more scaling ablations. We tried some different, say, pivot tokens. Maybe that's a good name for this weight token that we insert to get the model to think for longer. And essentially, weight worked the best. So we tried alternatively, and then the model might be alternatively, what is a different way to solve this question or something, and go on and try a different solution. We also tried just inserting or not inserting any string and just forcing the model to think for longer. And weight generally works best and is also pretty short, pretty intuitive, I think. Great. This is interesting, I think. If you rejection sample, then performance, you actually get negative test time scaling. So what's happening here is, again, we have accuracy on the y-axis, so performance on Amy or something, and then thinking time on the x. And if you sample until a model has a certain length, then you get a negative scaling trend. And the reason for this, if you look at the actual traces, is that often very long traces tend to be ones where the model got something wrong. Then it got lost in reasoning back and forth, and that's why the trace is very long. So if you just rejection sample until for a certain problem you get a very long thinking time reasoning trace, then it might actually be a pretty bad one because the reason the model took so much time is because it was wrong and it got stuck in some reasoning loop and didn't really arrive at the final answer. So I thought this is an interesting result. Obviously, rejection sampling is just interesting for analysis. It's not something we can use really at test time because that's pretty expensive. You don't want to sample until you get a certain reasoning length. Yeah. Cool. I want to briefly go over some limitations. So three that we'll take a look at, or I guess just two: flattening and the context window. So one thing, if we want to scale this further to hopefully one day have these models think for weeks or months on a single problem and solve these really ambitious problems that we looked at the beginning, P equals NP or other really hard problems that we might care about, then how do we get there? How much more research do we need starting from here? And this alone definitely does not get us there. So one big issue is that eventually we hit token limits. So here on the y-axis, again, accuracy on Amy or something, x-axis is thinking time. And sequential scaling with budget forcing here, obviously we get positive scaling until around, say, 10,000. And then it drops. So it goes down with this dashed line. And the reason here is we use this on a model with a limited context window for this plot. And so when the model hits this context window limit, say 16,000 or whatever it is, then it automatically gets the wrong answer and can't think further. So the performance would drop. And of course, we can increase the context window to say 130,000, and then maybe it would continue increasing. But the bigger underlying issue here is that with these models, increasing context window gets increasingly expensive. And so it's very hard to just increase the context window. And we need probably some better method to get the model to continue thinking without just an ever increasing context window. So some of the latest models, they're using summarization now, which is one way to get there. So at the end of the context window, it summarizes or compacts its previous context and then starts again. I think these are the kinds of methods we need to solve this flattening issue, context window issue. And then the other issue is that even if we solve the context window problem, performance might not always get better. Say we let the model think for a month. Is it actually going to be better than if we just let it think for a week? And to get around that, it's probably largely also a training problem. How do we train the model to actually use its thinking time properly? Another avenue to potentially solve that is combining sequential scaling with parallel scaling, which we briefly touched upon. So here are two parallel scaling methods in this plot as well, rebase and majority voting. So majority voting we already covered. Rebase is a very similar method that uses some tree search in addition to majority voting at the end. And both of them let us scale further here. So we have sequential scaling, but at the same time, we launch multiple of these sequentially scaled reasoning traces in parallel, let the model think for very long, and then we aggregate them at the end with either rebase, which does some tree search over them, or just majority voting. So we just take the most common answer of the model. And both of them let us get to better performance, and of course also with more thinking time, more compute, because now we're launching things in parallel. So I think these are exciting directions to pursue further. How do we get this to scale more? To briefly recap what we covered, we started out with a high-level goal of getting models that are really good at reasoning and test time scaling, and thinking about what is the minimal, simplest recipe to get there. So I see this as a really great baseline as well for getting there, improving further in the future. So probably forcing the model exactly how many tokens to use is not the final solution here, but it is a very simple, very good baseline to start from. And then we can think about more complex approaches where the model itself maybe decides the budget and tells the user how much it thinks it would need for this task or things like that. So we covered budget forcing for test time scaling and our small data set S1K, 1,000 really hard samples for eliciting reasoning capabilities. And together, this gives us the S1 model. Thanks. Feel free to take a look at the open source repo on GitHub if you want, or the paper, and I'm happy to answer any questions. Otherwise, I can also give some more content if there are other things people are interested in.